Okay, hello everyone. Tell me that you can hear me and we will start. Okay, awesome. So great to have you everyone and welcome to the Web3 Devs Underground Community Meetup. My name is Amit Shilo and I'm managing our wonderful community alongside our amazing team of volunteers and supporters. We are honored to welcome you all with us today. Before we dive in, I would like to briefly introduce you to our community. So we are a community of Web3 developers and builders founded on the open source values by Shauli Rejwan and Roy Yosherov. Since we have started 3 years ago, we have consistently hosted in-person events, bringing together some of the brightest technical minds in the space. We're committed to delivering top-tier technical content to the global Web3 community. We're thrilled to have you all with us today. To stay in the loop for future events and updates, please follow and subscribe to all our platforms. We're active on Luma, Meetup, X, YouTube, Telegram, and more. All available on our website at web3devs.org and easily accessed through the QR code on the top of the screen. So you can get directly to our website through there. A special thanks to our community sponsor, MasterKey VC, an early-stage venture capital firm focused on infrastructure and deep tech across the Web3 ecosystem, with a team of 16 world-class cryptographers and several other technical experts, led by our managing partner, Shauli Rejwan. MasterKey operates across all major crypto hubs. And now, without further ado, I am honored to pass the mic to our esteemed first speaker of today, Ben Kaufman, to introduce himself. Just a moment, Ben. Let's see that we can hear you.
Yeah, can you hear me well?
Awesome. Great to have you, Ben. The mic is yours.
Yeah, all right, thank you. Yeah, let me just share the screen for the presentation.
Sure thing.
Yeah, the presentation is visible, right?
Awesome, we can see it well.
Yeah.
Yeah.
All right. Yeah, okay, so yeah, I'll just start. Yeah, so thank you everyone for joining. My name is Ben Kaufman, and today our subject is Bitcoin miniscript and how we can use it to actually make Bitcoin programmable as it should be. Yeah, so let's just start with just a very brief introduction about myself. I'm a Bitcoin open source developer. I've been working in the Bitcoin space for quite a few years. I think in Bitcoin specifically from around 2019 that I've started doing open source contributions. I've mostly worked on Bitcoin wallets, especially cold storage and self-custody wallets like Spectre and Bitcoin Keeper. And yeah, my goal has been for a long time to make tools that make it easy to use and especially safe to use. Yeah, with this short introduction, I think we can just start with the subject of the talk and why this talk even. So the reason of this talk is that Bitcoin is the most important digital asset and the first programmable money, the first money that we can actually code. But this programming part, this coding part of Bitcoin is not used as much as it could be, right? Most Bitcoin wallets are using just the tip of the iceberg of this programming functionality. And this is mostly because script, the programming language beyond Bitcoin, is very fragile, is very hard to use. We'll see it a bit later in the talk, but there are a few reasons for that. But the main issue that we have is that Bitcoin is programmable, but this programmability is hardly even used. So how can we make it more common and actually take advantage to the fullest extent? So let's start first with a very brief understanding of how a normal Bitcoin wallet works. So in this talk, I'll assume that the crowd is mostly advanced or intermediate, but not really beginners. So I'll not go into what is UTXO or what is the seed phrase or what is public key, private key, digital signatures. I'll assume that people are just at least familiar with these concepts. If not, in the Telegram group, I've shared a few resources. You can see over there like links for the website called, for example, Learn Me Bitcoin, or for example, in Bitcoin Wiki. You can get familiar with all these concepts. So if something isn't clear of these more basic ones, you can just go there and see. But yeah, let's just start. So a Bitcoin wallet normally works in the following way. We start with a seed, with the seed phrase, the mnemonic phrase, these 12, 24 words that everyone is kind of familiar with. Then from that, we generate individual public and private keys. And these private and these public keys that we generate are then going into scripts, into Bitcoin scripts. And then they turn into addresses. The exact mechanisms of how to turn script into address, hashing it and everything, it's not the core of this talk. But the important point is to understand that a normal wallet, just what's called a single key or a single sig wallet, works by creating various private keys, then creating the public keys of these, then putting them into Bitcoin scripts, which simply say, okay, you just have this single key and you need to provide a digital signature that proves ownership of that key. And then we turn this script into address. So just briefly also about what Bitcoin script is. So script itself is the programming language of Bitcoin. It's a very simple and small stack-based language, which means that you basically put certain elements in a stack and evaluate them. The final evaluation is either true or false, either can spend the coin or cannot spend the coin. This evaluation of the script language of each UTXO is done by each node in the network for each transaction, which is why it's also good that it's very limited, that it's very small, because we want to limit the computation that every node in the network has to perform. We can, I'll briefly show what the script language looks like so you have an idea of how it visibly looks. So it's basically constructed from these opcodes, from these instructions, or objects. Like object would be like the private, like the public key, or a hash, or a certain pre-image. But this is basically what it would look like. So it's a bunch of these opcodes with values, and each opcode does certain things. Op if, that evaluates an if statement, true or false, right? Or false, whichever, right? So we have a lot of opcodes and they can perform different functionalities. So let's return to it. So Bitcoin script in general, it's a very simple programming language, but it's also very basic. It's very raw, we can say. So in a normal, again, let's return to our normal Bitcoin script, what it looks like, what a normal Bitcoin wallet actually looks like. So as we said, we start with a private key that generates a public key, right? That's all comes from the seed, but basically private key generates public key. And this public key is then going into a script. With a normal single key wallet, it looks something like this. So the script that is locking the coins is using, well, instead of actual public key, it usually uses pub key hash. So essentially it looks like this. Op dup, op hash 160, the hash of the public key, then equal verify, and then checking the signature. And then the user has to provide the actual public key and the valid signature in order to spend the funds. The script will then evaluate based on these two. So it will use the public key to check that it equals to the hash that was provided. And then it will check the signature with the check sig. All right, and then let's go further with the more advanced wallets. So with the usual, for a Bitcoin wallet, we usually have just two options that are the main ones in normal Bitcoin wallets. We have a single key, which is what we discussed so far, and we have the multisig option. The multisig option is very similar, but instead of just having one public key and one signature, we provide, let's say, up to X public keys, and we demand Y signatures. So a common example would be to a free multisig where we have 3 public keys, and then we just demand 2 signatures, and then the object multisig helps us verify that they match. It consumes the signatures that are provided, the requirement of the 2, the public keys, and the total number of keys. And from there, it will just check if the multisig transaction is correct or not, if the user could have provided the signatures that are enough to these keys. But that is all. So multisig is not something special. It's not hard-coded into Bitcoin in any way. It's just a script, right? So single key does have certain things that are special to it, especially with Taproot, but we will not get into that. But just to understand, everything is essentially script. For conceptually, everything is essentially script. So a multisig is a script, a single key even is a script. So why script is hard? What is the actual problem that we need to solve? Because we said Bitcoin is programmable money. We showed that it's programmable with this script. We showed all the opcodes. There are a lot of them, and we can do a lot with all of these. But the problem is that to do things safely, script itself is usually just too much. So example, if we want to have certain conditions, there are many ways that we can write conditions. We can use bool or, for example, or we can use op if. We can use various various opcodes to achieve the same thing. So let's say one wallet will do one thing, another wallet will do the other thing. They will not match anymore. So compatibility between wallets with just script becomes very difficult. Another issue is that script is very tricky. It has a lot of edge cases. For example, one of the most well-known ones is an issue with object multisig, which consumes an extra element from the stack, which means that basically all multisig transactions have to include an extra byte of data, an extra code of data there, which will be consumed with all of the other elements. This is not because it's actually used for anything, it's just a bug in script. So if you don't know about this small issue, for example, or if you don't know about this edge case, you'll be in problems. So script is not perfect in any ways. It's very raw. As we saw, it's actually working with opcodes which are hardly readable for anyone. And you have to actually track how everything moves. If you move things around the stack, if you swap objects, if you hash objects, you need to understand what every opcode does to the very minute details. So making sure that it works well is extremely hard. So now that we understand what are the issues with just using script, let's talk about what is miniscript. Miniscript, we can think about it. You can see what it says on the screen, but just, for example, let's think about it as Lego block, as taking script and making it into Lego blocks, right? So instead of using this very complex thing we call script, we push a few components of script together, which are usable in a certain way. Let's say we want to make a logical OR. We take certain opcodes, we put them together, we give them the name OR, and this is now OR in miniscript, or this is a certain functionality in miniscript. So miniscript is basically just taking script components and putting them into building blocks. So these building blocks are then used to actually make script more usable as miniscript. So now instead of having to actually deal with all the minute details of script, we have higher level building blocks, and these building blocks are much easier to read, much easier to understand. and much easier to use across different wallets. So now instead of having to understand, okay, what this exact opcode does, a wallet can just analyze the higher level blocks of miniscript, and with that, basically show the user the right interface of how to spend, of what they need to actually interact with their coins. So before, let's just understand how miniscript works. So miniscript actually has two layers, which are common. Miniscript is made of the actual miniscript, which is the lower level. We will see a bit later in the presentation, but we'll first start with the higher layer, which called the policy language. The policy is basically the more readable. It's not exactly human readable, but it's definitely developer readable language of how coins can be spent. So instead of saying, what happens is that you write policy as a developer, then the compiler generates miniscript, and Bitcoin sees the script itself. So it's basically a three level of compiling. We start with a policy, then we have miniscript, and then below we have the Bitcoin script that actually goes on chain. So policies, the way it works is it's what developers actually interact with. So developers can see miniscript, can read miniscript, but they don't really write miniscript. A developer will usually not be writing miniscript directly, simply because there is no reason to do it, and that a compiler can do it way more efficiently. So what developers actually write is called the policy. I'll show in a moment what it actually looks like. But just to understand, the policy is the description of how you can spend coins. So let's say you want to spend with Multisig. You write a policy which says that you can spend with 2 out of 3, and then that compiles lower into miniscript, and that compiles even lower into Bitcoin script. So we'll see how all that works in practice a bit later. Let's see just a few very common policy fragments. There is the PK, public key. That means just like a single key. It requires a signature, right? If you provide a public key inside, and it requires a signature. A thresh is like a multisig. You say a thresh of like a threshold of 2 out of 3, either keys or conditions, right? So there might be a condition inside it that evaluates to true or false, and that needs to be satisfied as part of this threshold. Then we have and or, which are basically and both conditions need to be correct, or one of them has to be, at least one of them has to evaluate to true, or has to be satisfied by the user, by the spender of these coins when they create a transaction. So you create a transaction, you need to satisfy these conditions. Satisfying just means providing the signature that is needed, provide the pre-image of a hash or stuff like that usually. And then these pieces, together with a few others we'll see a bit later, let you do a lot of different custody models. So whatever it's multisig with certain special conditions, or we'll just see later all the examples. So as we said, policy evaluates to miniscript and then evaluates to script. The policy is what developers write. The miniscript is something that is definitely deterministic, and script is the actual thing that goes on chain. The most important thing that there is to understand is that policy is what developers write, but it's not necessarily always evaluates to the same miniscript. It always evaluates with the same compiler to the same miniscript, but a compiler might evolve. So we might have, or we might find optimizations which make the policy evaluate to a miniscript which will work cheaper or more efficiently than before. And that's why policy is written by the developer, but then the compiler optimizes it into the right miniscript. We do not have a guarantee that the policy will always evaluate to the same miniscript in the future with different compiler versions, which is why when the user is interacting with miniscript, they have to save the miniscript as the descriptor and not the policy. Then let's see how miniscript miniscript actually looks like. Let's understand what miniscript is. So miniscript compared to the policy is much more accurate in representation of the spending conditions. So let's say that miniscript says that you want to spend with an OR condition. There are various ways to have an OR condition in miniscript, and the compiler just needs to find the most optimized way to do an OR condition in this specific policy that the developer wrote. So let's just see what miniscript more or less looks like. So miniscript code looks something like this. So instead of having just an or an and, you can see that we have and V, and B, or B, or C. So all of these are just different options for an or an and condition, etc. But these all are just, it looks very much like the policy. It just has a little bit more detail, which explain to the compiler how to exactly map things into script in the most optimized way. So one more thing that we should talk about in miniscript is time-based conditions. This is, sorry, just a second. So one more thing that we should talk about in miniscript is time-based conditions. It's another capability which is hardly used today in Bitcoin custody. It is used a lot in, for example, second layer solutions like Lightning or Arc, but it's not really used in actual, let's say, individuals or businesses self-custodying, simply because, again, as we said, it's very hard to define these conditions. And then if it's not for a specific protocol that has a lot of engineers working on it, it's usually not, it's usually just too hard for the average user to manage. But miniscript makes these time-based conditions that are available for us in Bitcoin readily available and very easy to use. So instead of just saying that we want a specific signature or a pre-image of a hash in order to spend coins, we can say different spending conditions based on the time that passed. We can say that one key can spend any time and another key can only spend on 1st of January 2027, or we can say that if that on the 1 million block, one key can spend the UTXO, and in 1,000 blocks later, another key can also spend it. So basically, we can define different conditions based on time or blocked height that is passed. And in Bitcoin in general, in Bitcoin script, we have two opcodes that are used for time locks, for time-based conditions, CTLV and CSV. So one of them is for absolute time locks and one of them is for relative time locks. But what does absolute or relative time locks actually mean? So absolute time locks mean that a certain condition is satisfied at a specific block height or timestamp. So I can say that in the 1 million block, something should happen, something should evaluate to true, or that when the timestamp of the blockchain is reaching, let's say 1st of January 2027, then the condition should be true. Or we can have relative time locks, and those become valid after a delay from the transaction confirmation. So from the time you have received a UTXO. So let's say I have a wallet, I received to it a coin. At the moment I received to it a coin, a timer is starting. Let's say a timer of 1,000 blocks or a timer of 1 year. And when this timer passes, something happens. Let's say that another key becomes available, or the coins themselves are unspendable until the time passes. We can define certain conditions on how the coins are spent relative to the time that they were received in the wallet. And in miniscript, these different conditions, these absolute and relative time locks are both available. The absolute one is used with the after keyword, and the relative time locks are used with the older keyword. So as we said, after is basically representing CLTV, and relative time locks are represented with older, which is CSV. If you'd like to search on the exact opcodes, there are a lot of specific details and differences between these. I will not cover them to more than we've done right now. Just one last thing is that an important difference is that CLTV time locks are basically unlimited in the time that can be specified in them. So you can say that in 30 years, a certain condition should be evaluated to true. And with an older statement, so with CSV, it is limited in time to about a year and 3 months or so. You can understand why, because certain formatting of the timestamp that is specified, but we'll not get into it here so much. Yeah, just one more thing is that the absolute time locks are very common to schedule certain events. So for example, a very good use case for absolute time locks is Anchor Watch and Bitcoin insurance policy. So Anchor Watch has this Bitcoin insurance where they insure you, let's say, for 1 year. They have a policy that they agree with you for 1 year. And after that, certain recovery conditions become available using Miniscript. So what they do is they use absolute time locks to specify the specific dates in which the policy expires or all of that, so that these conditions become available. Relative time locks are used more for certain cooldowns or safety delays or certain recovery mechanisms that you want after for each individual UTXO. So when you don't care about specific dates, like with Anchor Watch, they have their expiry date of the policy, so they care a lot about a specific date. But when you don't, when you do something that is, for example, for your own self-custody, you might want to use relative time locks and have it for each specific UTXO. This way you have to move them a bit less if you want to renew the time lock conditions or that sort of stuff. So Miniscript in practice is used, as I said, for certain inheritance tools, or for example, and a good example is Anchor Watch insurance policy. That is a very clear use case of how Miniscript can be used in the wild. But also we have certain inheritance tools that are using it, or certain advanced wallets that we will show in examples a bit later on. But the idea is that it allows very complex conditions that were possible before directly with script, but were just impractical in a lot of cases. So let's see a few Miniscript examples, and for that I'll use the website from Israel developer at Ishimoni, which is called Miniscript Studio. Wait, let me see. Yeah, Miniscript Studio here. So let's start. I'll just show the slides like this so we can jump easier between these and the Miniscript Studio. So let's start with the Miniscript examples. So we'll show the policy and then we'll show how it compiles. So the first one would be a simple single sig. What does that look like if we want to write it in Miniscript? So it turns out you can do it, and very easily. You just write the public key condition, PK, and you specify here we have the names for it, for example, the name of the person, but in effect, it has to be the actual public key. So either a raw public key or an extended public key, an XPub. But here goes the actual public key. If we just copy it and move it into Miniscript Studio and hit compile, you can see that here it replaces this name Alice because it's already predefined in its key variables. You can see that Alice maps to this specific public key. But it's also possible to use extended public keys. For example, you can see here that we define this testnet key as an extended public key. For simplicity, we'll just use the normal public keys here in the example. Sorry. So for example, when we compile it here, we see that the Miniscript for it is the public key, which is represented here by Alice, but in the actual manuscript, it shows the exact public key that is used. And it's super simple. It looks exactly the same. It's just PK and the public key. So this is, again, just to clarify, this is policy here, and here it's miniscript. But here they look pretty much the same, simply because it's such a simple condition. It is just a single key wallet. You have the public key, and you need to provide a digital signature for this public key in order to spend it. As simple as any Bitcoin wallet in existence, basically. In actual script, it looks like this. The Alice, the public key here, again, that goes, you can see the raw script here, but here it's like the compiled one that is easier to read a bit. So you can see here, Alice is just the public key for Alice, really, and just object-sig. This is all of it. And in the actual address generated from it, this is the address generated from this script that is generated from this mini script that is generated from this policy. It's a lot, but it's not, it's just these three layers. Just the policy layer compiles to mini script, compiles to actual script, and goes on chain as this address. So let's move on to the next example, which would be just a 2 of 3 multisig, a very simple multisig use case. Let's see what that compiles like. So when we compile that, you can see that instead of thresh, what it uses is this multi keyword. So the thresh keyword exists in policy, but doesn't exist in miniscript. In miniscript, it compiles to either multi or and or conditions. So in certain cases, it will usually use the multi condition, but certain cases turns out that it's more optimized to use or conditions in the miniscript, even though the thresh keyword is used in policy. This is why we say that the policy is the easier one that developers write, and then we let miniscript compiler figure out what is the most optimized way to implement this in actual miniscript. And we can see that this miniscript is then turned into these opcodes here. You can see it a bit easier here. So we push the number 2 here, we push each of the public keys, we push the number 3 to the stack, and we check, we do check multisig, which basically will check all the signatures that are provided in the transaction that tries to spend from this address. So this is the actual address that is generated from all of this. So again, you can see that it's very simple. It just compiles here the condition of threshold of 2 keys out of these 3 options, out of these 3 public keys. Here it compiles to the actual multi condition, which is, again, just let's say a multisig condition of 2 out of these 3 keys, 1, 2, and 3. And then these compiles into the actual script of pushing the number 2, of pushing each of the public keys, pushing the number 3 of the total keys, and then checking the actual signatures. So let's see a simpler thing. So multisig, where 1 key is always required. This is a bit more advanced, let's say, example, because this is something that is very hard to do without miniscript. So this simple single key is something that every wallet is doing already. Multisig, 2 of 3 multisig is something that a lot of wallets already offer with just a script template. We've seen it because it's so simple. And then let's move to something that is already requiring miniscript to do properly. So the example here is that Alice's key is always required, while we have 3 keys, Alice, Bob, and Charlie. Alice key is always required, and we can use it only with Bob or Charlie key. So it's a 2 out of 3, but Alice is required to sign. So if only Bob and Charlie sign, it will evaluate to false. It will not be possible to spend. It's useful, for example, if we want to have like friends that help you self-custody, that kind of are security guards for you, but they cannot spend your coins. So the way it works, you can see in policy, it's very easy to read as a developer. It's just an and condition, so we require both sides. This is one side, we require which is Alice key. And then the second side that we require is this OR condition. This OR condition includes either Bob key or Charlie key. That means that either Bob or Charlie has to sign, and Alice always has to sign. And just to see what it compiles like in Miniscript, so when we paste it here, you can see that it compiles to this AND V and OR C. Again, there are various ways to use OR condition in Bitcoin, right? So there are various options for an OR condition in Miniscript, which is why we have OR C, OR B, different conditions where the compiler just figures out which one is the right one for this use case. The compiler, its goal here is to save us on fees, right? So do the script in the most efficient way, and this way it will choose different ones in different times. So if we compile it here, so let's just see here, it's just an AND, as we said, PK of Alice or PK Bob or and PK Charlie here. In Miniscript, it looks like this. So again, AND, OR, and public key, again public key, and then again public key. So it looks somewhat similar, just a little harder to read with the extra V, extra C here. But it looks relatively similar, and a developer can still understand it relatively easily. Then in the actual script, it looks like this. So you see here the public key of Bob, the public key of Charlie, and the public key of Alice. And you can see here the specific instructions. So in order to actually understand how everything here is evaluated, you need to understand how script takes, consumes certain objects, removes them from the stack, what it adds again to the stack. You need to actually go one by one and understand what is going on here. You sometimes need to either maybe write down the actual steps and how the transition of what the stack looks like at each step. Again, this is why it's much harder to do with script, and why Miniscript is just so easily readable, especially as the policy language of it. So let's move on to the next example. Now we introduce time locks here. So here, this is just the time lock for January 1st, 2027. This is just the timestamp of it, the Unix epoch timestamp for it. So if we want, the simplest example that I could think of with a time lock is that we want to be able to spend only after a certain time has passed. So let's say you have a normal single key wallet, just like any other wallet, but you want to force yourself to hold the coins for until the 1st of January 2027. Or let's say you gift someone coins, but you want to make sure that they cannot spend them before a certain time. Let's say your kids until they're 18, or let's say you give it to someone for their birthday and you want to make sure that they don't sell just too fast. You could use this policy to make sure that the coins are not spendable before that. And why they're not spendable before? Because we have an AND condition here, which requires two parts to be true. Both the key of Alice, so we need to provide a digital signature that will satisfy for the key of Alice, meaning only Alice can spend the coins at any time, and the after condition, which means that this here will just, until the timestamp here is, we arrive to this timestamp, until the blockchain timestamp arrives to this, we cannot spend the coins. This will always evaluate to false, which means if this evaluates to false, the end condition evaluate to false, and the coins are not spendable. But then once the timestamp has passed, this will always be true. So after January 1st, 2027, this will always return true. And then if Alice wants to spend, she just needs to provide a valid signature, and that's it. Both of these will evaluate to true, and Alice can spend her coins. So again, let's just see what it looks like in Miniscript and in script itself. So here again, you see, so the AND is used, PK is used, and the actual key goes in, and then after, and the timestamp. So again, it looks very similar. If we would replace this with just Alice, you can see that it looks really similar, just this V here and the V here, which is for verify. But it looks really similar, and it generally is readable, mostly. Right, let's paste it again. So, and then in the actual script, you can see that we use opcltv. and the checksig verify to make sure that both are satisfied. There's no actual end condition here because we just make sure that both of them are satisfied correctly. CLTV, and this is the timestamp encoded. But that's it. We just make sure that both of them are satisfied to ensure that the actual script is valid. And then this is just the address of what it looks like. Again, this script goes into this address here. So let's move to the next example. You can recover with only, so recovery key only after long delay. So let's say we want to have, the policy here is wrong. We can just edit it manually, but I'm sorry, but I forgot to update here the policy. So this is still the policy from the previous the previous slide, but that just gives us the chance to write the policy ourselves now. So let's just do it. Let's change this policy here from being only one key after a single time, after a specific time, to be this key anytime or another key just after the time delay. So let's see how it works. So right now we have an end condition with this key and the timestamp condition. What we want to do is that instead of requiring an end here, we want to have it as an or condition, because we want or this key can spend at any time, Alice key can spend anytime, or let's say that Bob can spend after this timestamp. So here we would say or condition or Alice anytime. And here we will use the end condition to say Bob key after this time. So it's either Alice after Alice anytime, or these two conditions, Bob and the timestamp that has passed. And now when we compile it, you can see that it actually compiles to the mini script, which again looks similar. Here we can say Alice just to make it look easier, and Bob. So you can see it looks very similar. And in the actual script that is generated, you can see that it checks Alice, it does updo, which duplicates here the result. But again, this is why it's a bit harder, because we need to understand, okay, this creates one, this duplicates the result, this evaluates it. So again, this is why script is a bit harder to reason about, and min script is very easy for us to just read or this condition or both of these. This is useful. So this example is useful, for example, if, okay, I have my own stack, but I want to be able to give a key to a friend, and then that friend can help me recover, let's say, in case that I lose my coins. So until the timestamp, until the time here, January 1st, 2027, I can spend anytime, and the friend will not be able to spend. So I have full control of the coins. Once we arrive to that date, if I lost my key or anything, then I can trust my friend to help me recover. But if we are close to this date and I don't want my friend key to become active, all I need to do is create a new wallet, which has a different timestamp, let's say January 1st, 2028 instead of 27. And I move the coins. I just use my key that can spend alone. I send the coins from this older policy to the new wallet with the newer policy. That's how we can make mechanisms which can help us recover, but still remain fully self-custody. Let's move to, here the right one. Sorry, so this slide, let's lead. But this is the one we just created, you can see. So an or condition and the end condition. So let's stop for a moment with the examples to just understand a very small thing in policy that we haven't discussed yet, which is probabilities. Every policy has the option to define probabilities for or conditions. So an or statement can say, I believe that the left side is 10 times more probable than the right side. By default, each side of an OR statement is assigned the same probability of just 1, and then we can ratio it. So the probability is just defined as this at and the number of likelihood in the probability. So the probability is assigned 9, and here by default, if it's not set, it's assigned as 1. Okay, so the default is basically this 1 and 1 probability on each side. Even if we say 2 and 2, this will mean the exact same thing, like 1 and 1, or without having them at all. It just means they have the same probability. But if here I assign the probability of 9 compared to the probability of 1, so this is 9 times likelier than this one. If we want to ratio it, we can say that this is a probability of 2, but this is a probability of 3, for example. So we can do certain probabilities, and according to these probabilities, or why they're important, the probabilities, simply because the compiler will then find the most efficient way to compile it to account for these probabilities. So it will prioritize the more probable spending condition so that it's cheaper to spend it. It will optimize the actual script that is created, the mini script, and then the actual script created to prioritize the more likely spending condition. So, and by prioritizing, what I mean is that it will ideally try to make it cheaper, even at the expense of the less probable spending condition. So let's say here with the previous example of recovery key after a delay, that here we want to say that I most likely I will spend by myself here, or Alice will spend by herself, but there is the possibility that Bob will spend after this time. But we tell the compiler here that it's 9 times or whatever times more likely that Alice, we don't have to be specific, because 9 times or 8 times it will compile to the same thing. But we just say here that, okay, we are pretty sure that Alice will spend alone, that Alice will spend alone. But so prioritize this and make it as cheap as possible for Alice to spend by herself. But there is a chance that Bob will spend, so we also need to include that, but it's not likely. So if it costs a little bit extra, then that's not too bad. And then we can see that this is actually compiles to different things. So let's go here, paste this policy. You can see that here it uses ORD and the conditions here. So let's just replace it, Alice and Bob for readability. You can see here that it compiles in this manner, so OR, D, PK, and V. But if we change it and move the probability of 9 to this side, meaning it's almost, there is very low likelihood that Alice will spend by herself. It is more likely that Bob will spend after this time. Then we tell the compiler to actually, okay, you know what, prioritize Bob. Make sure that Bob can spend cheaper, even if the spending of Alice will be more expensive. By more expensive, just to make it very clear, by more expensive, we mean that they might need to provide more bytes in the transaction. The transaction becomes bigger, that makes the spending a bit more expensive due to fees. So here we can see that it changed. Now it uses an and/or condition. In the mini script, we see that it no longer uses this ORD. Instead, it uses and/or and prioritizes this condition first. So it puts this one, the Bob key first, and then only here at the end it puts Alice condition. So you can see that and/or means first do an and operation, then do an or operation here. And this again just compiles to a very different. Let's compile it here again. This compiles to a different script. You can see the script looks like this here. If we change the probability back to here, you can see that it compiles to a bit of a different script. So these are probabilities in miniscript. It just means, okay, optimize this spending condition or optimize the other spending condition at the expense of the other one. So let's continue with the last two examples of how to use Miniscript. Very common examples lately, which are an expanding multisig and a reducing threshold multisig. Let's see what they are. So starting with the expanding multisig, what it means that we want a multisig which expands over time, that instead of, let's say we start with a normal 2 of 3 multisig, but we want a new key to be added at a certain time. So let's say we start with a 2 of 3 multisig, then in 1 year, we want also another friend to be added to this multisig and have a signature in it. How we do that? So instead of using the OR condition here, what we do is use a thresh condition. So here we define thresh, which is a threshold condition. We say that we want 2 because it's a 2 out of 3, or eventually a 2 out of 4, but it's always 2 conditions that need to be satisfied in this threshold. And then we include the first 3 keys, Alice, Bob, and Charlie, let's say. Sorry, Alice, wait, sorry, this is the right slide. So we say 2, we include here Alice, Bob, and Charlie, right? So we say that Alice, Bob, and Charlie are always included in this threshold. So if Alice and Bob provide digital signatures, they will satisfy these 2 and allow them to spend. Alice and Charlie, or Bob and Charlie, any of them providing the right signature will satisfy this condition of 2 and allow them to spend. So a regular 2 of 3 multisig. And then we have here the extra condition that we are adding is an AND condition. So we want to add a condition which says that it will evaluate to true as well, only if Eva is providing her signature and this time has passed. So the specified timestamp has passed. So before the specified date, this will evaluate always to false, right? So Eva cannot spend because her condition, which is an AND condition, will always evaluate to false. And once this timestamp passed, then Eva can always spend because this will always evaluate to true for her. And then she's basically included in this 2 thresh. So even though this thresh has actually 4 keys, this key will always evaluate to false until the time passed. Let's just see it again in Miniscript, so you have a good understanding of what it looks like. So here in Miniscript, again, it uses a threshold here, it uses the AND here, and you see the after for the specific key of Eva. In actual script, you can see that this is already becoming quite longer and quite more complicated. So not just the 3 keys and op check multisig, this is already way longer and way harder to understand. You need to actually go over it and see what each action does to make sure that it works, what it does, and if it works correctly. But with Miniscript, it was super easy for us to write it. We just write fresh, we provide the keys, and for the special key that is activated later, we do an AND condition, provide the key, and the condition of the time here. And the last example I want to show here is a reducing threshold multisig, which is very similar. It's just that instead of becoming a 2 out of 4, we start with a 2 out of 3. Multisig. So how we do that with Miniscript? Again, it's super similar to the previous example. We start with a fresh condition, threshold condition. We provide the 2 requirement here, so we need to specify 2 of these. But how can these 2 become 1 later? Simply by making this last condition here, which will always evaluate to true after the timestamp has passed. So we have all the 3 keys here, but once the timestamp passed, this will always return true. So one of these will always be true already. So Alice can spend alone, Bob can spend alone, or Charlie can spend alone once this timestamp has passed. Again, in Miniscript, it will look like this. So you can see it fresh, very similar to the previous one, but just without Eva's key and without the AND condition. So always when this is true, return true for it. So essentially it will work the same way as if we had 1 threshold here and just the keys without the condition here of the time. Once the time passed, this is exactly what happens. And in script, it will look like this, as you can see. So one of the last things I wanted to mention is a very important design principle in Bitcoin script and Bitcoin in general. An important principle to keep in mind is that Bitcoin script is designed in a way that it can become only easier to spend over time. It can never be harder to spend over time. We cannot have a multisig that becomes that starts as a 2 out of 3 multisig, but then later is turning into a 3 out of 3 multisig where all of the participants have to sign. This is simply impossible. And it's because the principle that's guiding all of these and actual practicality is that you cannot make scripts harder or more strict. You can always make it only easier or keep it the same way to spend the coin, but it's not possible to make it harder over time to spend your coins, only easier or more options to spend. This is basically also because in script, if we have here a time condition, it will always evaluate to true after it. But if we say, for example, let's go to the recovery key as an example here. So you can see here, Alice can always spend, Bob can only spend after a certain time, but Alice can always spend. We cannot say, okay, Alice can spend until this date and Bob can spend after this date, but Alice cannot anymore. Alice has her branches, she can always spend. It's impossible for us to say, you cannot spend after this timestamp. We can only say, okay, now Bob can also spend after it, but we cannot change it so that we invalidate previous paths after a timestamp has passed. We can only open new paths. So I think this is a very good already summary of what you can do with Miniscript, what it looks like, how it works, and how it actually helps us in simplifying the Bitcoin programmability and making it actually easy for wallets to use. And if you want to actually use it or see which wallet support it, then you can see the following wallets. So there is Bitcoin Core, there is Liana, there is Bitcoin Keeper, and Nunchuck. Bitcoin, the important difference is that Liana and Bitcoin Keeper support a lesser extent of Miniscript. So they do not support all variations of Miniscript because, as we saw, Miniscript is very versatile. It's easier and a subset of the script language, but it's still very versatile. So showing all the options that are in Miniscript to the user is extremely difficult. Bitcoin Core supports generic Miniscript, and I believe that Nunchuck also supports generic Miniscript or most cases of valid Miniscript in their app. So if you already want to experiment actually doing self-custody with Miniscript, you can do it with these wallets. So just a quick recap, a quick summary before we go over to questions or anything that you want to say. Bitcoin was always programmable money that we knew. So from the moment Satoshi created it, he created it with the script language. You could always do, well, not all of these conditions because, for example, time-based, we're not present in the original version, but added in soft forks. But you could always program it in certain ways. And now you can do a lot of it. Miniscript is basically a subset of script that makes it practical, safe, and predictable to use in different wallets and actually use it for your self-custody coins. And as we mentioned, it is, I believe, the foundation for more advanced and reliable self-custody structure. So with all these examples, everything you could do with it, these expanding multisig, these reducing thresholds, these are all real use cases that people have asked for, that people have talked to me about, that, okay, can I do something like this? Can I do this special condition because I have this lawyer I want to give a key to, I have my children I want to give a key to, but I don't want them to spend just yet, to be able to spend the coins themselves just yet, but maybe later or maybe together. All of these conditions can actually be used in real life. So we want to make sure that they are all available to people. And Miniscript is what brings it to consumers. Yeah, that is it. So I'll open to any questions if that is possible, Amit.
Yeah, sure. So first of all, thank you so much, Ben. This was amazing. I have some questions more about you, I see, but yeah, just let's start with that. So Ben, how did you start your way in the space, and what got you into it?
So how I started, it was quite a few years ago. I was a software developer, quite a beginner, and I had a friend that just asked me, "Hey, do you know what this Bitcoin thing is? I have a few questions." So that got me curious because I had no idea about what he's even talking about. So that what got me kind of curious, started learning, started reading about it, and followed into this rabbit hole um, of Bitcoin. Then if you want from the technical perspective of how I started in it, it's reading a lot, or well, in the past there was much more limited resources. I guess right now you have a ton more resources that didn't exist when I just started. So I will share in the Telegram group. I already shared one of them. I can share a few more later on. But you're just read about it, just learn from YouTube, and then actually getting into development is just have fun with open source projects that you like, find something that you find useful, and go into their GitHub and play with it.
So that's actually one of the next questions. So, what is a book, podcast, or channel or website that you have used and recommend to people that joining your specific field or friends that you want to get into?
So podcasts are usually less technical. There are good podcasts, but they're usually not very technical, but they're still good. Stefan Levers is one of my favorites as a Bitcoin podcast. But for more technical resources, I'd say that you'd have to read a bit more or see certain lectures of more advanced Bitcoiners. You can find a lot of them online. I'll try to compile some recommendations and send it into the Telegram group. In terms of books, I really like the Jimmy Song's book. I think it's called Programming Bitcoin. It was very good to kind of understand a few of the concepts and the actual math behind stuff. You don't have to be an expert or a cryptographer or to do any of that, but it's always good to understand what happens behind the scenes.
Awesome. Okay, next question. What is your favorite thing in what you do today?
My favorite thing, I honestly just enjoy working in Bitcoin, but the favorite thing is probably to hear from people that are actually using something that I built or something that I help building, seeing people that actually trust it, and sorry, and actually use it to secure their financial future, right? Hearing from people that I helped is extremely motivating.
Okay, amazing. Next question. Okay, what are some mistakes that you think developers should avoid, or is one piece of common wisdom that in your industry that you completely disagree with?
So I guess, let me think about it. So one thing that a lot of people say is that multisig is too complicated and that people should either just use a single key or passphrase with single key and shouldn't go beyond that. I think this is already completely false. When I joined the space, there was not yet Miniscript even, and multisig was still very hard to use. I agree, but I think now there are so many solutions to do advanced Bitcoin security very easily, even for consumers. You can either use certain tools, you can pay certain services to help you with that. But I think that the biggest mistake that people in the field are making is they just say, just trust a single key. It's the easiest thing to not mess up, and tell people to avoid going forward with more advanced or more secure solutions. eventually, right now, I think it's getting easier and easier. Miniscript is still a bit hard. I agree on that for a lot of users, but just using normal multisig and even certain subsets of miniscript is becoming quite easy. So I think people should avoid this recommendation to just stop in a very basic and not so secure setup like a single key wallet and explore further options.
Okay, I have two last questions. So a bit unrelated, but let's see if it's interesting as well. So what is something that you're currently learning that has nothing to do with your work and you would like to share?
Well, not much really. It's something I like learning new languages, which is something that I learned that is not related to my work, but I'm not sure how relevant this is here. So beyond that, not much. I mean, mostly I'm focusing on Bitcoin and software development. So I guess one thing that in software development is just how to most efficiently work and adapt to the new AI environment, which is a very important subject. I'm definitely no expert on, but I try to learn and adapt.
Are you using AI in your work, by the way?
All the time now. It's got to a point where AI is just boosting the productivity in ways that I didn't think we're even like I couldn't even imagine probably 2 years, 3 years ago. I didn't imagine that AI will ever get to these levels. So I was completely wrong, and I try to adapt to it now.
Awesome. So last question is if you have any tips for developers that you think might help them become better along the way. Yeah, sorry, my internet kind of froze.
So yeah, I couldn't fully hear you.
Yeah, sorry. So one tip that you would like to give to developers that you think is valuable and you would have loved to hear when you started.
So developers in general or in the Bitcoin ecosystem specifically?
Whatever is your take.
Okay. Yeah, I think the biggest thing that I found, or well, let's say in Bitcoin space or any space that you want to get specifically into, I'd say working on open source is a great way to get started. It's a great way to show your work, to show what you want to know how to do, to work together with others and just do cool stuff, see them in the wild, and eventually it can help you professionally finding a job if that's your goal. But it's also just a lot of fun and gives you a lot of experience working in open source and contributing to open source projects.
Awesome. So thank you so much, Ben. This was fascinating and real fun to ask you some questions as well. And for the audience here, I hope it opened your appetite because we're starting in like 2 minutes the next talk with Ben Weinberg. So Ben, thank you so much for joining us today. We will continue the discussion in the Telegram group and probably ask you for some more resources. But thank you so much for your time. This was amazing. And yeah, see you next time.
Yeah, thank you for inviting.
Sure thing. And Ben, are you with us as well?
Hey, guys.
Hey, great to have you, Ben.
Thanks for having me.
So, for everyone who needs a coffee quickly, you have 2 minutes before we're starting. In the meantime, we can set up the presentation. And yeah, great to have you, Ben. Thank you so much for joining us today. You can start with introducing yourself if you would like. We do have a recording, and yeah, the stage is yours.
Let me just pull up my slides here. Google Slides.
In the meantime, if anyone from the audience has any questions for us about the community or anything else, feel free to just like ask them in the comments or in the Telegram group. I'll try to answer in the meantime. I'll even do that.
Okay, I think it's here. You guys can see?
Just a moment. Okay. Awesome. I think we can see it. Let's take a minute and then we can start.
Cool. I wouldn't mind adding one more thing as well. One of the questions someone asked Ben before me, resources he used when he was getting started. I want to add two more that I used back in the day.
Awesome. Yeah.
On the topic of Bitcoin, there's a book, it's a bit older now, called Mastering Bitcoin by a guy named Andreas Antonopoulos. He also has one called Mastering Ethereum. I haven't read the Bitcoin one. I've read the Ethereum one, which was excellent. Like, could not recommend that book and anything by Andreas anymore. It's all like on GitHub. It's free. Yeah, it's really, really good.
Well, awesome. We will really appreciate if you can share the link later on the group. Yeah, we're eager to get more good resources to learn from. Okay, I think we can start. Ben, do you want to present yourself first?
Sure. Yeah, thanks for having me. My name is Ben Weinberg. Been in the space since about 2017. Actually got into space when I was living in Israel, going to meetup groups there. Was previously a software engineer at DraftKings on the blockchain team, and before that was building an NFT marketplace called Ephemera. Today I work on the Axelar team in developer relations. I'm also a community organizer here in Toronto, where I'm based out of, for general tech meetups. So anyone in Toronto, feel free to hit me up. More than welcome to attend. For today, we're gonna go over a few things. The topic of the talk is cross-chain non-EVM to EVM. So the background is going to be a bit about the differences of operating in the EVM ecosystem versus the non-EVM ecosystem. EVM, for the record, stands for Ethereum Virtual Machine. So these are blockchains, like obviously including Ethereum, but that also run the Ethereum virtual machine, which means for the developer's purpose, you can write Solidity smart contracts on them. They also have like the Ethereum JSON RPC for any node operators. So in addition to Ethereum, these includes chains like Binance, Smart Chain, Avalanche, Polygon. Most of the major layer 2s are all examples of chains like in the Ethereum ecosystem operating the Ethereum virtual machine. The non-EVM ecosystem are chains, well, that you're not really writing Solidity contracts on there, that have really come to prominence over the last few years. So examples of like Solana, for example, is like your kind of premier high throughput layer 1 that's completely different than Ethereum in the way it's constructed. You write smart contracts there in Rust. Another example is Sui, which is what we're going to be working with today. So I want to quickly talk a bit about the differences of EVM versus non-EVM. We're then going to do a handful of things involving walking through building the simple ERC20 token for the EVM ecosystem. We're then going to build a coin in the Sui ecosystem with the Move programming language. So kind of for the non-EVM ecosystem. We're then going to make use of something called the Interchain Token Service, a tool built by Axelar to basically move that coin that we build from Sui to Ethereum. and we'll wrap it up there. Cool. So a bit of background. I started touching on it already, of the Ethereum virtual machine versus the SWI virtual machine. So Ethereum virtual machine, as I had mentioned before, are for chains that developers can write Solidity in. The way it's designed, there's a bit of nuance between different EVM compatible chains versus EVM fork chains. But for the purpose of this example, we're just going to be working with Ethereum itself. The SWI virtual machine, on the other hand, is quite different. Programs or packages are written in a language called Move. A bit of context on it. SWI is a project that came out of Libra. For those who remember, a few years ago now, when Facebook was getting into the space, they had a project called Libra. That project ended up splitting into a few different ecosystems like Aptos, Say, and SWI. They pioneered a language called Move, which is very similar to like Rust, but it's kind of more geared specifically towards smart contracts. We'll get more into the SWI side of things in a bit. So our objective, as I said before, is to build out two different fungible assets, one on Ethereum and one on SWI, and then we're going to move that asset from SWI to Ethereum. We're going to essentially bridge it. So let's walk through EVM tokens very quickly. I'm assuming most people are familiar with building Solidity contracts. We're going to go a bit more from the ground up when it comes to the SWI side. But for the Solidity side, it's very straightforward. We're going to have a smart contract called interchain token. It's going to inherit from the interchain token standard, which is a standard that Axelar has, which allows you to basically have functionality built into the token that makes it movable between different chains. It's also going to inherit from the standard ERC20 standard, which has the familiar functions like minting, burning, total supply, among other mainstream functionality, which all are fungible tokens on EVM chains use. And it's going to inherit from Minter as well, which will basically allow the role of minting the token. So for our token to be compatible with ITS, all what we need is really these two functions, mint, which we'll use to move the token into Ethereum, which will be triggered by our bridge, and burn, which is what we're going to be using when we're moving it out of Ethereum. Those are really the only two functions we need to make our token compatible on the Ethereum side. And you'll see we're going to restrict both of these functions to an account that has the minter role. So that's really it for the Ethereum side. It's meant to be very straightforward. We have a contract which inherits essentially from ERC20, making it compatible to the ERC20 standard, so we can have all our standard fungible functionality on Ethereum. Getting more into the SWI side of things. So SWI is a blockchain built for speed, essentially. That is the main way to think about it. Everything that we do, all the good, the bad, and the ugly from the developer experience side, comes back to actually being able to operate on a blockchain that can handle a tremendous amount of throughput. Solana is very similar. So I want to talk a bit about the outline of dealing with these kind of caveats in the SWI ecosystem. We're going to also talk a bit about what's called the treasury capability, something very critical for interacting with coins on SWI. And then we'll actually spin up our coding editors and build some stuff out together with Move. Sweet. Okay, so as I said before, SWI is a blockchain that's built for speed. And how does it actually do that? The main thing which SWI has in comparison to chains in the EVM ecosystem is the ability to do parallel execution. In contrast, in chains in the EVM side, like Ethereum, they're limited to only sequential execution. Okay, so what does that actually mean for us as developers? Well, first of all, parallel execution, what does that actually mean? It means that we can handle multiple transactions going in at once. So the throughput of transactions going in on SWI is astronomical compared to other chains out there. For us as developers, what does that mean? It means that in SWI, everything is declared as an object. Why is that? Because packages, as it says on the slide, don't have storage the way smart contracts on the Ethereum ecosystem do. So in Ethereum, you might have, let's say, our ERC20 token that we were just looking at before has one address, and that one address has storage for the way you're interacting with it. So for example, it might have like a mapping of I own 10 units of this token, Amit owns 20 units of this token, and that is actually stored in a mapping on the Solidity contract itself, all deriving back to that one address. That is not really the case with Sui. In Sui, we have a package, the way we have our ERC20 token deployed at a certain address on Sui, which has all the different functionality built into it. But every item that is being produced from that Sui package is actually stored in a different object. So it's not like we're always deriving back to one specific address on the Sui blockchain. Rather, that one coin is going to be interacting with many, many, many different objects. Each interaction with that coin will derive a new object, and each object has an object ID, kind of similar to address. So we can look up like an object ID on the Sui Explorer, the way we can look up an address on the Ethereum Etherscan Explorer. The way you can think about it, if two transactions touch different objects, they can be executed at the same time. That's really where this speed of Sui comes in. Whereas in Ethereum, one state tree, any transaction that might touch a transaction can only be executed one by one. So in Sui, we're dealing with objects, whereas in Ethereum, we have like everything kind of based around one smart contract at a given address. So that's one caveat that we have to deal with when we're building with the Sui ecosystem. It's a bit of an adjustment at first, but you get used to it fairly quickly. Another big difference is that there's no concept of a message sender in the Sui ecosystem. In Ethereum, you might have we have this global variable which everyone's familiar with called the virtual machine's familiar with called the message sender. How does that work? Well, in the EVM ecosystem, every call is technically part of a stack. And every call made on that stack comes with a message sender, which basically means I am the person who triggered that transaction. And this is really useful for things like security requirements on a contract. Like you might want to limit some action on a smart contract to that message sender, to the person calling it, as opposed to any other random address. Whereas in Sui, you don't interact with the call stack the way you do in EVM chains. Rather, each program that gets deployed, there's like a preset of communications with move modules. So I'm basically telling right from the get-go to my Sui package, like, hey, these are the different modules which you can interact with on chain. Whereas in EVM, there's like this notion of a arbitrary .call where anyone can interact with anyone, like complete composability. And in Sui, it's a bit more limited. Why? Because it goes back to what I was saying before, that idea of parallel execution. The runtime only knows which objects it can interact with from the get-go. And when it knows who it can interact with, it allows the chain to be able to handle transactions quicker, really going always back towards that North Star of higher throughput in the Sui ecosystem. The final point, and we could have a full talk just on Sui concepts. I'm really cherry picking just a few here, which I think are most relevant to the example I want to show. But the final point I want to mention is this idea of capabilities. So this is kind of like, it's a segue from our previous point of there being no message sender. And kind of what's the remedy for being no message sender? Because this idea of figuring out who called the transaction, like it is super important in smart contract development. So what is a capability? A capability is simply, as most things are in Sui, an object. By the way, this is all similar to like accounts, as they call it in the Solana ecosystem. These objects can be thought of as like keys that basically grant you permissions to serve any restricted actions. So it's kind of a replacement for like an access control, which anyone from the EVM ecosystem might be familiar with. So capabilities, as with any objects in Sui, can be distributed. So they can be owned or they can be shared across multiple different actors. One example of a capability which we're going to use, if I go back to the previous slide, is the treasury cap. Treasury cap is short for treasury capability. And this is going to be a very critical feature which we need to interact with our coin, because whoever holds the treasury capability is going to be able to actually mint and burn tokens or units of our coin on Sui. Cool. So let's actually get into the move code as a whole. And we're going to kind of break this down as simple as possible. And then I'll run over to the editor and we can actually spin some of this up. So this is kind of the starting point for any SWI move module. For anyone coming from the Rust ecosystem, this probably looks like familiar syntax. Apologies for anyone who this is maybe a bit less familiar to them. But we start from line 1 here. We have a package, which is called mycoin. That matches like the package name, which we have in a .toml file, kind of a configuration for our SWI package, which I'll show in a bit. But we have a package here called mycoin, and then colon my custom coin. So mycoin is the package name, which holds a module called my custom coin. So the module lives in the package. And the kind of structure to think of it is that a package can hold many different modules. And the module is what contains all of our functions and our structures that our coin will have, kind of the building blocks of the coin. If we go to the next line here, we'll see that we then make use of a separate module from SWI called coin. Kind of like how we were inheriting ERC20 before in our Solidity contract, which will give provide our interfaces for all of our token functionalities on the EVM side. Here we're going to be pulling in the coin module to have some out-of-the-box functionality for our fungible coin on SWI. And you'll see the coin module makes use of something called self, which basically says, hey, allow us to have access to everything inside the module called coin. In addition, we're going to be pulling out the treasury cap, which stands for treasury capability. It's basically just a struct, a relatively simple struct, which I'll show you in a bit, inside the coin module, which remember, we're going to make use of that for essentially whitelisting myself in this case, but it could be other actors to mint and burn our token once it's our coin once it's deployed on chain. Sorry, I'm trying to use the correct terminology here. In EVM, they use a token as a term. In SWI, it's coins is the term that's used. The final thing we do here is we have a marker type. It's essentially just a struct called my custom coin. This is essentially the type which our package will be in the eyes of SWI, the type of our object. Remember, in SWI, all objects have types. It's a bit different in Solana where the accounts are non-typed. What our my custom coin type has is an ability called drop. Now, the ability is a bit different from the capability that I was just talking about before, like the treasury capability. Remember that's before, like the kind of a set of permissions which an address or an account might have. Whereas the ability is much more limited. These cannot be customized the way capabilities can be customized. I believe there's only like 4 or 5 different types of abilities which SWI gives us out of the box. So it's like copy, store, key, and drop, as we're using right here. And what are we using drop for? We'll see in a bit, but the high level is that it's going to allow us to discard values in our package as we build them. So back to here, we're essentially just defining the bare bone capabilities of our SWI package, kind of like we were doing before with just the contract. My name is inheriting X at ERC20 in the Solidity file. The next thing we want to go do here is once we've actually defined, and I'm going to show this all in one segment at the end. But the next thing we want to do now that we've actually defined the name of our package and we've made available the coin module that we want to use is we want to make an initializer. So this is a function which is going to be called as soon as the package is deployed, and it's going to run some pretty basic functionality for us. You'll see that it takes 2 parameters, the witness, which is of type marker, the marker being my custom coin, which we defined here in the previous slide, and a context, mutable context. So I'm going to focus more on the witness for this. What the witness is doing is in the form of being of type my custom coin. It's basically going to be used to, in the next line here, to call the create currency function. This create currency function is defined in the coin module, which we imported up top, and it's going to return the treasury capability and metadata. And what the witness is going to be doing is basically telling the create currency function, like, hey, the only person that can be creating this brand new currency that we're making is the my custom coin module. Essentially, our package is the only entity that can do this one-time call to create the currency. We don't want anyone else to be able to do it except for our package. And it comes in the form of type my custom coin to kind of identify our unique package. The context, as in most Rust-based programs, is just providing information about our calls. So like who sent it, when. We're going to need that in the create currency. So we pass in these like 6 or 7 different parameters, including the witness and information about our coin. So 6, like how many decimal places does it have? What's the symbol? What's the name? Similar to Ethereum on this side of things. Once we've called the create currency function and we've actually created our coin, we're now going to have available 2 new objects. One, the treasury capability. Remember that ability or that kind of role which will allow someone to mint and burn units of our coin, as well as the metadata object, which represents data about our coin. So the first thing we want to do is this metadata object, freeze it, which when we call public freeze object, we're essentially making the metadata immutable. So no one can change it. Naturally, we don't want that because we don't want anyone to be able to change these critical components of our coin, like its name, its symbol, its decimal places. So that's the very first thing we do is freeze the metadata. The next thing we want to do with our treasury capability is actually transfer it to the sender, to whoever called this, whoever made the call to this initializer, which is going to be me in this case. And this is basically saying like, hey, caller, you can now have the treasury capability, which means you can now mint and burn units of the coin. I know this may sound a bit contradictory. I was just saying, if you recall before, there is no message.sender, but there is this context.sender. There's a bit of nuance here. Message.sender is in Ethereum in context. They have similar functionalities, but technically they're different. For example, like message sender and in the EVM ecosystems, like an implicit global variable, which comes right out of the box. Whereas this context.sender is a more explicit parameter, which you notice we've defined ourselves here as an input for this function. So they're similar in the way they're being used in this case, but there is nuance. There's quite a bit of nuance to the way these are actually are under the hood. The final function which we have for our move coin here, and this is really all we need to make it compatible with our bridging service, is the mint functionality. So minting will take 4 different parameters. The first thing it's going to take is a mutable treasury cap. So the treasury capability, which I've just transferred here to the sender, would be me in this case. I basically need to pass that treasury capability. Remember, the treasury capability, as with everything in SWI, is just an object. It's going to be an actual value, which we can see on chain, the way you can see like any address. So we need to specify that. And this treasury capability is going to be derived back to me. Like, it's public, anyone will know what it is, but only I can actually use it. If someone else were to try to use it, it wouldn't work. And it's going to be of type my custom coin. Notice it's a reference, a mutable reference, I should say. Why is it mutable? It's because the total supply, which is actually a field in the treasury cap struct, is going to be mutated as soon as we call this function. Why? Because we're minting, so the supply will go up. So because this supply gets mutated, changed, essentially, we need to mark this parameter here as mutable. Why is it a reference? Because we don't want to forfeit the ownership of the treasury capability. In move-based contracts, if I am passing in a parameter the way I'm passing like the amount or recipient, I'm actually passing along ownership of that parameter. Now that's fine for some of these less important parameters, but for the treasury capability, that's really not fine for me to be passing ownership, because that means I won't have the treasury capability anymore. And I don't want to give it to someone else. I want to hold it myself. So how do I get around that? I just pass a reference to it rather than the actual value itself. If I were to pass it, I could technically just return it, in which case I'd still have it. It's just a bit unnecessary, or I'd have to freeze it or send it to someone else. All things that I don't want to do. So that's where why the reference comes in. The other two parameters are a lot more self-explanatory. The amount, which is just how many units of the coin do I want to mint, and the recipient, which is who's going to be receiving the coins when they're minted, as well as the context, which we covered before, just parameters relating to the or components relating to information about the call. So like who sent it, what epoch was it sent at. Yeah, so then when we actually execute the mint function, we're going to be calling mint on the coin module. Remember the module which we implemented at the we made available at the very beginning. Mint is going to require two parameters, like the key, the treasury cap, like are you actually able to mint it, the amount, and then the context. And then once we've minted, we'll actually pass the amount to the intended recipient. And we're going to see all this in action. We can actually probably go to that right about now. Actually, let me briefly mention ITS quickly just before we go into this. Just because I'm going to be referencing it a lot as we roll this out. So I want a very quick high level. Once we've actually deployed our SWI coin, which we just went through, as well as our EVM coin, which we went through at the beginning, we're going to integrate it with Interchain Token Service. All what Interchain Token Service does is it leverages general message passing, basically the ability to send messages from SWI to Ethereum or any other chain to basically say, hey, I'm going to burn this coin on SWI, and then I'm going to send a message to Ethereum, which is going to essentially mint it on Ethereum. That's actually how we're going to move the coin from SWI to Ethereum. It's going to be doing this through a token manager, which ITS will be deploying for us. So it's a token manager is a separate contract on Ethereum or package on SWI, which is kind of facilitating our relationship. So when I move my coin, which we've just built from SWI, I'm going to send it to my manager on SWI, which will lock the coins for me. It doesn't have to be lock. It could be burning it as well. I'm choosing lock in this example. And then on the Ethereum side, it's going to be minting it. And vice versa, when I go back for Ethereum, I can burn it on Ethereum and then unlock it on SWI. So that's all we really need to know about ITS for the context of here. I want to focus more on the move side of things and building our SWI coin, but we'll be interacting it with this at the very end. So let's actually go to our code right now. And let me make it a bit bigger so you guys can see what's called. I mean, come off mute if the code is too small. I can't see the questions once I'm on here. I'm assuming this is fine. So I'm going to start with here. Our .move file, which is our coin that we put together before. So we can see here the module.
I'm not sure you're seeing what you're seeing, Ben.
Oh,
I'm
can you not see it?
Interchain Token Service ITS.
Okay. Yes. So let me fix the screen sharing. Cool. Can you guys see now the code? Yeah, I'm assuming you can see now.
Okay, yeah, now we can see
Yeah,
it.
you can see it. Beautiful. Okay, and if the code is too small, let me know. I'll make it a bit bigger.
If you can make it a bit bigger, I think.
A bit bigger? Okay.
Awesome. Yeah, thank you.
Here we go. Let me make it prettier. Okay, so all we're looking at here is just a recap of everything we talked about on the slides, just in its full form. So we have the package name, we have the module, my custom coin. We're importing the coin module here from SWI. This is built by the Miston Labs team, the creators of SWI. We import self, which basically contains everything in this coin module, as well as the treasury cap, the treasury capability. Remember I was saying before, the treasury capability is really just a struct, which contains two items. The unique ID, the object ID, which it will have on chain, because remember everything in SWI is an object, as well as the total supply of the coin in existence. So that's the treasury capability. We mark our type as having the drop ability, which we're going to use momentarily. We then have our initializer. We call the create currency function here from which is defined in our coin module here. It checks to make sure like, hey, is the caller is the caller actually going to be the witness, or it's going to actually enforce essentially, not it's a bit different than a require statement. It's going to enforce that the witness calling this create currency function is our my custom coin package, which we've just created up here, our module here. We call this, we got our treasury cap, we got our metadata, we freeze the metadata, we then transfer the treasury capability to the sender. We then have our mint function, which we'll interact with in a bit. So that's just a recap of how the coin package works. It's as simple as it can get, and you can find explanation for all this on the SWE documentation. Now, for what we're going to actually do with it, let me close this. I have made several scripts, so we're jumping into the JS world now to actually interact with this and eventually send it to Ethereum. So the first step which we have here is the deploy script. So I ran this before. Bear with me for the Murphy's Law of live coding as I try to run these scripts. I'm going to try, hopefully these all work. If they don't, I ran it before and we can go through a working version together. But let's try run this. So if I run node scripts deploy.js, it's going to run through all this logic here. All what I want to focus on for this script right now, while this builds, is what's going on here on line 20, as well as on line 21. And this is essentially how we interact with Miston Labs SWE transactions JavaScript library. Basically, the ability to, okay, sweet, it worked. Basically gives us the ability to interact with SWE packages from a JavaScript layer. You can just get this through NPM. And the way it works is we have to essentially create a new transaction object, which is what we're doing here on line 20. We then have to do some action with this transaction object, which is what we're doing on line 21. So calling like the publish function. Now, when we call this, that's not enough. Nothing's actually going to happen on chain until we go here to line 26, where we actually sign and execute the transaction, which is essentially just like broadcasting the transaction on chain. So these 3 steps here are critical. We're going to be repeating these throughout every single script that we have available. So create the transaction object, do some action on it. In this case, it's publish, and then sign and execute. We then, the last things we do here is just siphon through the logs that we get in their response from signing and executing to get our package ID, which is essentially the address kind of our mycoin.move package. We then also log the treasury capability. So what we got here on line 9, this treasury, remember, it's just an object on the SWE blockchain, just like everything else is essentially an object. Remember, there's no storage on this package the way there would be a storage on the Solidity contract. Rather, everything that's created here is just its own object, including the treasury object. So I can even just grab this ID. I can go to the SWE Explorer. Hopefully this pops up. It does. And I can see this object ID. You can even see, let me zoom in a bit. It corresponds to my unique, my custom coin marker type in its name, in its identifier. So it's a completely unique object treasury capability for this specific coin that we deployed. And we can see it on SWEScan the way we can see our package ID. I highly encourage anyone who's really serious about SWE to take a look at the Explorer. It's very different than like using Etherscan, just because of all the object. Like if I go to this transaction, you can see all the objects which are being updated, as well as the balance change. We'll familiarize ourselves a bit more with this in a bit. So that's all what's going on in this deploy script. Now that it's run, we have our package ID, which represents the mycoin.move file, and we have our object for our treasury capability. Cool. The next thing we want to do is, now that we have a coin on SWE, let's actually mint it. So we have, let me close these. We have a script for that as well. Similar to our previous script, we have our get wallet helper. I know I glossed over this before. This is just to basically get a key pair that we can interact with anything on SWE. We use that key pair to get my address. We, again, create the transaction object, just like we did before. Remember the 3 steps: transaction object. Step 2, we do an action. So before it was .publish, this time it's .move call instead. And then step 3, broadcast the transaction with the sign and execute transaction. Cool. So the move call that we're actually doing here is going to be on our my custom coin package. So we're going to be calling the mint function, which we defined here before. We pass in the 4 parameters that it requires. So, or 3 parameters in this case, because the first one's just the context. So we pass in the treasury object. What is a treasury object? It's what we logged here before. We pass in 1 just for the amount of coins that we're going to be minting, and then the recipient's address, which will just be me. So that's the call that we're going to be making. We then log that we're sending it. We then broadcast the call. What does it mean when we actually broadcast it? We need a signer, which is the key pair that we got here on line 10. We then pass in the entire transaction object, which is making this move call. So we pass it in here on line 29. And then I just mark optionally to show all the objects changing just for my own logs. So let's run this guy and hopefully it works too. So node scripts mint.js coin package ID. Let me grab this guy right here. It then needs the treasury. Why? Because remember the treasury, we're going to be passing it in here. Remember the treasury capability. We cannot mint a token unless we have that treasury capability specified. So that treasury capability is in the form of this object right here, 0xA41. Pass that in here, and that should be all we need. Coin package ID is not specified. Let me see, what did I do wrong here? Murphy's Law of live coding. Coin package ID. Let me try to pass this in again. Coin package ID. Oh, typo. Should be package. Cool. Now, once we run this, we see my token balance at 1, got incremented, and the new coin, the mint object ID. So this is self-explanatory. Our balance incremented by 1. But what is this coin object ID? Remember, unlike in Solidity, there's no mapping in our smart contract or in our package that says like, hey, Ben owns 1 coin. Rather, every new unit which is created is its own object. So this object of 0x26A81 represents the 1 coin which I now own. If I mint again, there'll be a new coin object ID representing that new unit of the same coin that I still own, but just in a new object. It doesn't have to be 1. One object can be like 1,000,000 coins if I want, but it just represents that transaction where that it goes back to that transaction where that coin was created or was minted. Yeah. So next thing I have for us, now that we've deployed the coin, we've minted the coin, now let's actually integrate it into ITS. So remember this slide that we had here before, this slide that we had here before with the manager, which we're going to eventually use to lock the coin on Sui once we're moving it out. We need to actually set that all up now. So that's in this integrate Axelar script. So again, same steps as always. Sorry. We get our wallet, we create a transaction object, we do something with that transaction object, which is just a move call. It's a call to actually create that coin manager object. So the buddy who facilitates our relationship and will be locking our coin, we're going to actually create that here. We're going to create a locked one instead of a mint burn, which basically means that when we're moving our assets out of Sui, we're locking it instead of burning it. We then make a second call with this same transaction object to actually register the coin with ITS. This call needs several parameters, including just information about our coin. So what is the name of the coin? What is the symbol, the decimals? What is the object ID of the coin? So what we had here before, this representation of the minted coin, it needs that as well. And then the manager. which is what we created here on line 17. We then broadcast the transaction the same way we always do, and then we can log that our registration was complete. And then the most important thing that we need here is our token ID. The token ID this is an ITS specific thing. It's basically going to be not an object this time, but it'll look like one when it's logged. But it's going to be the representation of our registered coin on ITS. So let's run this script. So node scripts integrate axillars, I chose to call it, and it's just going to need one parameter, which is the coin package ID, which we had from our first script when we published. Hopefully I didn't do a typo this time. Sweet, it runs, and now we have our token ID. So this 0x377 is how our coin is registered by ITS. Why is this important? Because if someone else were to go and register this exact same coin with ITS, they could, but we might want like the canonical representation of that coin's integration with ITS. Now, two more steps here before we can actually, or one more step before we can send it. Deploy remote token. This script is going to actually make a cross-chain call to deploy our EVM token on Ethereum. So remember what we were doing at the very, very beginning, the Solidity coin, the Solidity token. You'll notice I didn't actually build it myself. All what we built was the Move coin on Sui. We never actually built the Solidity one. Just to make things easier, I'm going to send a cross-chain call through ITS to deploy that token for me on Ethereum. How does it work? I'll go to line 19 in a minute to explain it. But we call get wallet just like we always do. We make a move call with the transaction that we create here on line 23. That move call is going to be to get our token ID object, which we're going to actually need to specify to ITS because our token ID on Ethereum is going to have to correspond to the token ID on Sui. That's how they're going to be connected. Even though they're completely different, they're built completely differently, the ID is going to be what connects them. We then call deploy remote interchain token, which is a function which is defined on ITS. And we pass in several arguments, including our token ID's object, the Sui ITS object, the token ID object, which we had here on line 25, and the name of the destination chain, which is going to be Ethereum Sepolia. So once we call this, we'll actually have a cross-chain transaction that is executed. So let me write this up. Deploy remote token.js. This will need the coin package ID. It's going to be the same one as before. This one will also need the token ID. ITS needs to know what our token ID was, which we had logged in our previous command. Let me just find it. You know what? Token ID right here, 0x377. Sweet. So we now made a cross-chain call. And as we are speaking, this token is being deployed on Ethereum. So if we pause right now, let's kind of recap where we are. We have our token, which is deployed on Sui, and our token, which is deployed on Ethereum. And then for time's sake, I'm going to run through the last script very quickly. Now that we have two tokens deployed, the last thing we need to do is send it. I forgot to explain this before. Line 19, this my custom coin here. We use it again here. This is just the unique object representing our coin. So you'll notice that when we first deployed, we had a package ID for the coin. That is different than the object which we use. The object is what we use to actually hold value about the coin, which ITS needs to interact with this to actually interact with the coin. The package ID is more just holding the functionality of the coin, but in terms of data about the coin, we use the object ID. So we again call get wallet, we create a transaction again, we get our token ID, just like we did before for the deploy remote token. How do we get this token ID, I kind of glossed over it. We just called the token ID function from SWI ITS, and we pass in our hard-coded token ID, which we're just passing in the script call here. And then this returns a token ID object for the token ID. We then need to use our gateway channel ID. Okay, so when we're sending a cross-chain call, in this case, there's a few things that we need to touch on before we can actually send the interchain transfer. The first one is going to be the gateway channel ID. When we're making a cross-chain call, what we're technically going to be doing, ITS kind of did this for us in the last script. That's why we didn't have to worry about it, but we have to do it ourselves this time, is we actually have to broadcast a transaction from our gateway, okay? So what does that mean? It means that we need what's called a channel ID for our gateway. The channel ID is basically needed because, remember, in SWI, we don't have a message sender. We're kind of a lot more limited that way. So we need to pass in what would be the kind of like the message.sender as a parameter in our function that we're calling. So instead of relying on message sender in the function we're going to eventually be calling, which is prepare interchain transfer, we're actually going to be specifying who the message sender is, which is the gateway channel ID. I'm sorry to keep using message sender. It's the channel ID. It's just going to be kind of behaving as the caller. Cool. So we make this call here to get what our object ID is for the gateway channel. Then there's another interesting caveat that we have to deal with when we're dealing with SWI. Remember when I minted the coin a few minutes ago, it returned an object ID. So we had my token balance of 1, and then we had the object ID for that coin. If I want to actually interact with that coin, I have to, that mint of the coin, I have to pass in that object ID, 0x26881 and whatnot. What's the issue? The issue is that by interacting with that object ID, I'm therefore interacting with the entire balance that corresponds to that object ID. And the same principle applies here to paying gas. When we're calling this prepare interchain transfer, we're going to need to essentially specify a gas parameter, like how much gas do we want to pay? Why? Because the way the cross-chain component works is we pay gas however much we want, and then that gas is forwarded along to the destination chain to cover the gas costs of executing there. And we have to specify what that amount is ourselves as a parameter. Now, I don't want to spend all of my native SWI coins to just pay for the gas here. I want to send maybe 1 SWI out of the, not actually, but let's say the million SWI coins that I own. So how do we actually get just 1 SWI coin? Because remember, we're just dealing with an object ID, and that object ID corresponds to everything. So what we do is create a new object ID corresponding to just the 1 or 5 or however many I want to send. And we do that by calling split coins, which is a handy function which the Mistin Labs team has for us out of the box called split coins. So we pass in the coin object ID, essentially the amount of coins that we want to send. And sorry, I said gas before. This is for the amount of coins that we want to send, not for the amount of gas that we're paying. We're going to do this again for the amount of gas we're paying shortly, but the same principle applies. I'm not sending all my coins. I'm sending just a specified amount. I specify the amount by passing in the object ID of here and the amount of coins that I want to send. I then call prepare interchain transfer, which returns something called a ticket. What's a ticket? A ticket is essentially a stamp for our transaction. And the better question, I think, is why do we need tickets? It goes to the way upgradable contracts are handled in SWI. So if we think of the EVM ecosystem, you have a proxy, you have an implementation, the proxy points to the implementation, you upgrade it by swapping the implementation for a new implementation. What does that mean? It means that the old implementation is no longer reachable because you're only ever interacting with the proxy, which is pointing to a given implementation. With SWI, that's not the case. You can technically interact with old versions by accident or on purpose. So what does that mean? It means that when you're actually making a call to a program or to a package, you have to specify what version of that package do you want to do you want to interact with? And that kind of all being bundled as a part of that ticket. So we create the ticket here, and in that ticket in ITS, we don't need to specify the version here. The version of ITS will actually be specified. So we call this prepare interchain transfer, which takes all these parameters on like what coin are we sending, what's the ID, the token ID that we're sending, the name of the destination chain, any data that we're specifying along with the token, the name of the destination chain that we're sending it to, the raw name of it, as well as the gateway channel ID, which we created here before on line 40. That all gets bundled into this ticket object. And that ticket object eventually gets used to send the interchain transfer. So it's essentially a two-step process. We create the ticket, then we use that ticket to actually send the transaction. That sending of the transaction will then give us an interchain transfer ticket, which we generate with our other ticket. And then we can take that interchain transfer ticket and actually broadcast that transaction from the Axelar gateway. So we do that here. I'm going to recap all this. Sorry, I know this is a lot. So we have our interchain transfer ticket. We then have our GMP ticket. Remember, every ITS call is just a GMP call. So we take that interchain transfer ticket, then we make a GMP call. GMP stands for general message passing. How do we make that GMP call? It's two steps. We pay the gas, which is what I was saying before, if you recall, where we pay the gas on the source chain, and then that gas service gets used to actually handle the execution cost on the destination chain. So we pay that gas here. And then finally, we can actually broadcast a transaction with the send message call with the gateway. It's another package which Axelar has available. As soon as we call send message, the message will be picked up by an Axelar relayer and sent to the destination chain. And it's all done with the same design we had before. So we have one single transaction object. Where is it? Interchain transfer transaction right here from the transaction object, which is given to us by the SWE Mist and Labs team. We then bundle all these move calls into here. So this first ticket, this second ticket, this call to the gas service right here. It's all going into the same interchain transfer TX call, as well as send message here. Then in this interchain transfer call, we can call sign and execute to essentially broadcast it. So once we do this, that call will be broadcasted and sent cross-chain. The one thing I forgot to mention before is this destroy call. This destroy call is to essentially handle our gateway channel ID. Remember in SWE, because it's kind of a Rust-based system in the form of move, every parameter which we pass in has to be handled in one way or another. So it either transferred somewhere else, frozen, or in this case, destroyed. We don't need the gateway channel ID, so we make a separate call to destroy it. Without further ado, let me actually make the call here. Sorry, let's make the call here to fire this off. Interchain transfer.js. You can see I made several calls of this before already, just when testing. Package ID, same as before. We just get these from the logs from our previous transaction. Coin package ID. We then want to specify the token ID, which we had up above. Let me actually stretch this out to make it a bit easier for me. Oh, much better. Where is the token ID? Token ID. Where is it? Mint. Token ID. Oh, there it is. Coin registration. Sorry. Actually. Oh, sorry. I actually removed the log here back and forth. Why we don't see the token ID. Let me actually just, for time's sake, I'm going to go back to here because everything is in this transaction is exactly as we did it before. what we actually do here is we call the interchain transfer script. We pass in the coin package ID. We pass in the token ID. We pass in the name of the destination chain, Ethereum Sepolia. We just hard coded ourselves. We pass in the destination address. This notice is an Ethereum address at this point. The amount of tokens that we want to send, and then the coin object ID. Remember, this coin object ID is the object ID which was created when we minted our coin. So now, if I go to our Axelar block explorer, actually I have it open right here, we can see our cross-chain transaction going from SWI to Ethereum Sepolia. And let me make it a bit bigger. I can scroll down here to click on the transaction on SWI, which will take me to the native SWI scan block explorer, so I can see our interchain transfer being triggered from SWI right here. And I should be able to see here the balance changes. So MIC, my coin that I made, you can see a tiny amount because of the decimals here, but 0.001 is being deducted from my account, 0xA46 right here. So it's being taken from me. It's now going to be locked with the manager on SWI. And you can see all these objects here being updated in correspondence with what happened. I can now go back here to Axelar Scan, and I can click on the executed transaction on Ethereum Sepolia, which takes me to Etherscan, and I can now see 0xC5D, my address on Ethereum, receiving 0.001 of my ERC20 on Ethereum right here. I can also see the events for it. The transfer coming to my address. So one token being sent from SWI to Ethereum, and we can see both of these on the block explorers right here. And I think I'll wrap it up with that. I hope that made sense. All the code which we worked with here, I'm going to make available on GitHub. I'm happy to send it if anyone wants to play around with these scripts. It's very, very straightforward instructions. You should be able to run through these yourselves if you want to kind of play around with it, see it all happening on the SWI Explorer and on the corresponding Etherscan block explorer. And you can also play around with how SWI coins work as well. And yeah, I think I'll wrap it up there.
Awesome. Thank you so much, Ben. And that was impressive coding skills in front of an audience. So live coding skills. So thank you so much, man. I know you're short on time, so we'll keep it very short with the questions. So I'll start with, why is it useful to be able to interact with different versions of what you explained before?
Yeah. Like with ITS, what I was saying. Well, it's think about it with like Ethereum, right? We have upgradable contracts there. It's no different. The whole ticketing system with interacting with different versions is no different than having upgradable contracts on Ethereum. Now, why are upgradable contracts in general important? Well, many reasons. Like we release a version of a protocol and there's, God forbid, like a bug, which we need to quickly fix, or there's new features you want to roll out, the more likely case. So it just gives us a lot more flexibility on the developer side to roll out amazing new stuff while not changing the address.
Okay, awesome. I would like to ask you too this as well. So how did you start in the in this field or in the space?
Yeah, very long time ago now. I was I think Ben mentioned the same thing, but Ben before me. I was just learning to code at the time, and I was trying to do iOS development. This is summer of 2017. I didn't actually have a relevant CS degree at the time. I studied politics and business, and I was trying to do iOS development, and I kind of always felt a bit behind the eight ball. And then summer 2017 was like the ICO bull run, all this kind of crazy stuff going on. I was actually in Israel at the time when this was happening. And I started going to meetups, and my thought process at the time was like, okay, I can be like very behind in iOS as I felt, or I can try to be one of the first people to know to learn this pretty incredible new field that's up and coming. Ethereum was like 2 or 3 years old at the time. So I took the plunge, started learning Solidity, and kind of made that investment. Like, let's be one of the first people to learn this.
Amazing. And takes me to the next question. But in an industry that moves as fast as crypto, what is your personal filter for separating real innovation from hype, and what is really interesting to learn?
Yeah, I listen to whoever's on Web3 Devs Underground, and whoever's on there seems to be pretty legit. No, it's hard. It's really, really hard. There's some good podcasts that I like. There is, like DevCon, I had it on in the background here all day, but I'd almost say almost impossible. Like, a lot of the hype is not necessarily malicious scammers. Like I was talking about 2017, back in the day, there was a lot of just blatant frauds at the time. Nowadays, just because something is hyped doesn't mean it's a malicious scam. It might just not work. I'm not going to say any names or anything, but like, there have been some amazing projects with some amazing technology, which just quote unquote didn't meet the hype in hindsight. So it's really hard to say. Just because something does not meet the hype in hindsight does not mean that they're not amazing technologies worth looking at. So there is no real clear answer to that.
Okay, awesome. So last questions. So one tip that you have for developers that you think is a good time to share?
New developers or like more seasoned?
Let's start with new developers and then Web3 developers that are more seasoned.
Yeah. So for the new developers, I think it's a very relevant one now. I'm going to kind of piggyback off two things that you and Ben were talking about before. So for the new developers with AI, I'd say be careful. I agree with Ben, it's incredible. Like, anyone who's used like Cursor or anything, like, amazing tools. It does make life so much easier. But for new developers, be careful, because you can become overly reliant on it, and you kind of have to force yourself to struggle. Like, try walk before you can drive kind of thing. Like really learn the problem rather than have Cursor just solve it for you. Otherwise, you'll kind of never learn the fundamentals. For more seasoned developers, like what Ben was saying, like, contribute to open source projects is very helpful. Even doesn't have to contribute, like, just read the open source projects, familiarize yourself with the README, try actually interact with like scripts, like what I was just showing before, like just play around with the actual code to learn new stuff rather than just reading an article about it or listening to talk about it. Actually really get down and dirty.
Okay, awesome. Thank you so much, Ben. This was great advice. I'm sure our community will appreciate it. So thank you so much for joining us. I'll finish with thank you for everyone who's joined us today. We're going to have much more interesting things coming next year as well. So stay tuned. Join the Telegram group. Feel free to take part, ask questions, be involved. We're open source, and we're welcoming for all Web3 developers. We're here to help you learn as well. And like Ben mentioned, this is exactly the place to contribute and try your best to become a part of it. And yeah, thank you so much for joining us today, everyone. And thank you again, Ben. This was amazing.
Thanks, guys. Thank you.
So yeah, we're wrapping up for today. I'll give you a last chance to scan the barcode on top. It's not StreamYard, it's our website. And it has all the relevant links to our Telegram group, to our materials that are all on YouTube. And you can watch there all the previous meetups with all the amazing speakers we already brought. And yeah, stay tuned for updates about next year. We're going to have amazing things coming. And thank you again. Bye-bye for now.